Hello and welcome to a new video on IGCSE Physics Classified Paper 2. In this video, we shall be discussing the topic of circuit analysis. We will begin with voltage analysis in a circuit. Which statement is not correct for two identical lamps connected in parallel? So connected in parallel means that they look like this. We have a battery here or a cell. We have two lamps that look like this. And 1 coulomb of charge is going to move from the positive terminal. Like we said, this is conventional current. We just assume that it moves from the positive terminal. And then it will either choose to go this way or that way. So maybe the first coulomb of charge will go through the upper lamp, and then the second coulomb of charge will go through the lower lamp. Of course, this is not scientifically very accurate, but we'll just assume it is. We'll just imagine it is so that we can analyze the circuit. So 1 coulomb of charge takes 6 volts from the battery. Each coulomb of charge, for example, takes 6 volts from the battery. So we can assume that right before it enters, its voltage is 0, and after it exits, its voltage is 6. And as long as there are no lamps or resistors, there is no change in voltage. There is no potential difference. We just assume that. That is also not what happens in reality, because the wires themselves have resistance and so on. But we just assume that the wires do not have resistance in order to analyze, because otherwise it becomes very complicated and beyond your current level. So if this is 6 here, then the voltage here will be 6 as well. The voltage here will be 6 as well, because it has not yet met anything that consumes voltage. And if this guy is 0 here, if the voltage is 0 here, then the voltage must be 0 here as well, and must be 0 here as well, must be 0 here as well, and 0 here as well, and 6 here and 6 here as well. So like we said, 1 coulomb of charge only meets 1 lamp on its way to and from the battery. So what actually happens is that the voltage drop across the lamp, which we call the potential difference, must be 6, because the coulomb had 6 before entering and had 0 voltage after leaving. So it must have lost 6 volts. And this is the same here. So each lamp actually consumes 6 volts. And this is the advantage of parallel circuits, because in a parallel circuit, each lamp will consume the same amount of voltage as supplied by the battery. How is this different from circuits which are not parallel? So for example, if we have a circuit that looks like this, let's again trace the path of 1 coulomb of charge. Let's say that the battery here or the cell provides 6 volts again. So we should know that the voltage here must be 0 and the voltage here must be 6, because the coulomb goes into the battery empty-handed, without voltage at all, and then leaves the battery with the 6 volts that it supplies. And like we said, we assume that the wires do not consume any voltage. So this is 6 and this is 6. Here would be 0. Here would be 0 as well. Here would be 0 as well. So now 1 coulomb of charge has 6 at this point and has 0 at this point. And this tells us that the voltage drop between these 2 points is 6. So both lamps share the 6 volts. If they have equal resistance, what will actually happen is this guy will consume 3 volts. So the voltage here would be 3. And then this guy would consume the other 3 volts, so that the voltage here is 0. So now, if they're connected in series, what actually happens is that they share the voltage of the battery, as opposed to each lamp getting the whole 6 volts. So one of the advantages of parallel circuits is that each lamp gets the 6 volts of the battery, or whatever number of volts that the battery supplies. But in series connections, they have to share the voltage of the battery. So this might not be strictly relevant to the question, but it's important to understand this before solving any voltage analysis questions. Which statement is not correct for two identical lamps connected in parallel? The potential difference across each lamp is half the supply voltage. This is our choice, actually, because this is incorrect. They're looking for an incorrect statement, and A is incorrect because we just said that if they are connected in parallel, the voltage drop across each lamp is equivalent to the voltage gain across the battery. So this guy gets 6 volts and this guy gets 6 volts as well, equal to the 6 volts of the battery, because 1 coulomb of charge will either pass by the upper lamp or the lower lamp. It cannot pass through both because they're in two different branches. However, in the series circuit, 1 coulomb of charge will necessarily pass through both lamps. So they have to share the 6 volts together. Each lamp will take 3 volts from the passing coulomb. So in a parallel circuit, the potential difference across each lamp is not half the supply voltage, it is the supply voltage, or it is equal to the supply voltage. This is why A is the correct choice here, because it's the incorrect statement. Let's look at B, C, and D as well. So for 2 lamps connected in parallel, the remaining lamp still operates when 1 lamp is removed. This is actually correct, and it's another useful thing to talk about. One of the issues with series circuits is the following. If I have a fault in the first lamp for any reason and it breaks off, and by breaks off, I mean there is an open circuit here, right? So the current is no longer passing. The other lamp will automatically break off as well. It will stop working. There will be no light because there is an open circuit and the coulombs cannot pass from here to there. So there is no electric current and the lamp will not light up. However, in a parallel circuit, if one lamp breaks off or malfunctions for any reason, if it stops working for any reason, there is no issue with the other lamp because the current will still move this way. But instead of having the option of going here or there, it no longer has the option of passing through the lower lamp, but it can still pass through the upper lamp. So there will be a mini circuit here with just 1 lamp still working. So that's another advantage of parallel circuits, which is that if 1 lamp breaks off, the other lamps can still work. Similarly, in C, they can be switched on and off separately. This is a correct statement because if I put a switch here, if I open the switch, and by open the switch, I mean there is no current flowing, neither lamp will work. If I close the switch and I allow electricity to work, allow current to pass through, I mean, both lamps will shine. So either both lamps work or both lamps don't. However, in the parallel circuit, if I put a switch here and I call this switch A, and I put another switch here and I call it switch B, I can use A, I can turn A on and off to control the upper lamp, and I can turn B on and off to control the lower lamp. So I can switch them on and off independently. D says they remain bright if another lamp is connected in parallel. We said that this is also true because even if I connect 5 more lamps here, any number of lamps, each of them will get the 6 volts of the battery. So they will remain bright. So B, C, and D are correct, and A is the only incorrect statement. And we just showed why this is the case. Why are lamps in a house lighting circuit connected in parallel rather than series? So A is correct. No, excuse me. If one lamp stops working, the remaining lamps become brighter. No, I mean, they still work, but they don't necessarily become brighter. They still get the 6 volts. So they are as bright as they were before the lamp stops working. Less current is taken from the power supply. This is not true. The lamps can be turned off independently using switches. This is very, very true. This is the correct answer. When more lamps are added, their brightness decreases. This is incorrect as well, because like we said, if I have 5 lamps or 50, each lamp will still get the 6 volts of the battery. So the brightness stays the same. So the correct choice here would be choice C. The circuit diagram shows a 4 ohm resistor and an 8 ohm resistor connected to a 6 volt battery. What is the potential difference across the 4 ohm resistor? You might be tempted to do a lot of mathematics here, maybe get the current, or if you've studied equivalent resistance, maybe try to get the equivalent resistor or whatever. But this is all unnecessary, because we just said that 1 coulomb of charge is going to move up to here, and then it will either decide to go along the blue arrow, or it will decide to go along the green arrow. Either way, it gives its entire 6 volts to the resistor. So regardless of which path it takes, it only needs one resistor along the path and gives it the entire 6 volts. So without any calculations, you can say that the 4 ohm resistor is going to get 6 volts. So the correct answer here would be choice D. The circuit diagram shows a 4 ohm resistor and an 8 ohm resistor connected to a 6 volt battery. What is the current in the 8 ohm resistor? So in order to get the current, we're going to use the equation V equals IR. And we already said that the V here has to be equal to 6 because they are connected in parallel. So we just do a simple substitution. We put 6 here equals I times R, which is 8. So in order to get the current, I simply divide 6 by 8. I equals 6 over 8. This is the same as 3 over 4, which is 0.75 amperes. So the correct choice here would be choice C. The diagram shows a power supply with a constant electromotive force, EMF. It is connected to a voltmeter, a variable resistor, and 2 identical lamps, P and Q. Both lamps are lit. The resistance of the variable resistor is increased. The voltmeter reading remains unchanged. What happens to the brightness of the lamps? Like we said, the brightness of the lamps depends on voltage. And since they are all connected in parallel, no matter whether I increase or decrease the resistance or remove the resistor completely, they will all get the same voltage as the supply. So if this guy supplies 6 volts, then each of these guys is going to get 6 volts regardless of the resistance of the variable resistor. Therefore, the correct answer here is choice D. The brightness is unchanged. It is not affected at all by the resistance of the variable resistor. 4 lamps are each labeled 60 watts, 230 volts. In which circuit are the lamps connected so that they operate at normal brightness? So if they're labeled 230 volts, then they need 230 volts in order to operate. So in which circuit do they get 230 volts? Obviously in circuit B, because this is a parallel connection and each lamp is going to get the same voltage as what is provided by the supply. However, in all the others, there is a series connection. There are lamps next to each other, which means that they're going to have to share the voltage of the voltage supply. So B is the correct choice here. Identical cells and identical resistors are used to make the circuits shown. In circuit 1, the ammeter reads 2.0 amperes. What is the ammeter reading in circuit 2? Now, this is not an easy question. It's a tricky question. So let's try to work it out together. So this is one cell. So the voltage supply here, let's call it V. Okay. And the resistance here can be called R. In the other diagram, we have 2V, and we have R here, and we have R here as well. We want to know what the ammeter reading is in circuit 2. So what's the current in circuit 2? What's the total current, right? So in order to figure out what the total current is, we need to understand one concept which we shall elaborate more on in this same video, which is that if I have two branches like this, so if I have current I, and then I have two branches, we said that each coulomb is going to choose either to move along the green path or along the red path, right? So let's call the green current I1 maybe, and the red current I2. We should know that I is equal to I1 plus I2. Because these two currents split up, they come from I, the blue I, and then they split up, and then they converge back. So I2, the red current, and I1, the green current, will converge at this point here and merge together and form I again. So I is like the main current, and then I1 and I2 are branches of the current, components of the current split up to feed the two different resistors. Now, what is the value of I1 and what is the value of I2? So we know that this guy, this resistor here, gets 2 volts because it's connected in parallel. And this resistor as well gets 2 volts. Not 2 volts, like 2V, whatever V is. It's double the value in circuit 1 because we have 2 cells here as opposed to 1 cell there. So that's why I labeled the first voltage as V, or the first EMF as V, and the second EMF as 2V, because there are 2 cells. So each current is equal to V over R. So V equals IR, whatever the voltage is. Now, in the case of the first resistor, taking this part here, the voltage is actually 2V, and we want to get the current, and the resistance is R. Excuse me, the resistance here is R. So I, in this component here, would be what? It would be 2V over R. So this here would be 2V over R. And with the same logic, this as well would be 2V over R. So if I add these together, what is I equal to? I is equal to 4V over R. What about in circuit 1? In circuit 1, things are much simpler. I have V and I have R. So I is just equal to V over R. So if I compare this current, I equals V over R, with the other current, what do I notice? I notice that it's 4 times as much. The current in circuit 2 is 4 times as much as that in circuit 1. So they tell us that in circuit 1, the ammeter reading is 2. Then in circuit 2, the ammeter reading must be 2 times 4, which is 8 amperes. Like I said, this is not an easy question, but I do hope you understood how we solve. Moving on, we're going to talk a little bit more about how current splits up in a circuit and so on. A student connects the circuit shown, which switches must be closed for both the bell to ring and the lamp to light. So in order to understand this, you need to understand how the current flows inside a circuit. Like we said, the main current I would move out of the battery like this, and then it splits into I1 and something else here, which we don't care about for now. And then this something else is going to split into I2 and I3. So the total current is equal to I1 plus I2 plus I3. This isn't really relevant because we're not trying to calculate anything for now, but we want to know, in order to have the bell ring and the lamp light, which switches do we need to close? You need to understand that the currents meet up again. So this green current here, I3, is going to meet up with I2. And then they're going to form a current, which we don't really care about for now. But this current is going to meet with I1. And all of these end up forming I, which goes back to the battery. So what happens if switch 1 is open? Open means it's it's blocking the electricity. There is no electricity flowing. If one is open, then I itself cannot flow. And I is like the source of all the currents. So I definitely need to close switch one. Because if that one doesn't work, if that one is kept open, then there will be no current flowing through the circuit at all. So one is among my correct answers. What about two? Well, for the lamp to light, I have to close two as well, because otherwise the lamp won't light. So I need to close two. What about three? I also need to close three for the bell to ring. The only one that I don't really care about that I can keep open is four, because if four is open, I3 will be zero. If I3 is zero, that doesn't really hurt me in any way, because the I1, which is passing through the lamp, is still working, and I2, which is passing through the bell, is still working. There is still current flowing in these branches. So I don't need four to work. I don't need to close switch four. I just need to close 1, 2, and 3. So the correct choice here would be choice C. The diagram shows an electric circuit. When the switch is open, which lamp or lamps are not lit? Now, if the switch here is open, then there is no current flowing in this part, because the switch here blocks the current, it's open. Remember, closed switches allow electricity to flow, but open switches block electricity in a sense. So if this switch is open, there is no current flowing through S or T, but the main current will flow from the battery and then flow through R and then flow back to the battery. So R would still be working. So which lamps are not lit? S and T only are not lit. So D is the correct choice. The circuit shown contains 3 ammeters, X, Y, and Z. Which ammeter has the largest reading? So again, let's do our current analysis. The main current flows from the battery. Let's call that I. And then it splits off into I1 and I2. And then I1 continues along this branch, and I2 continues along this branch. And then they merge again to form the main current I, which goes back into the battery. So again, we need to know that I is equal to I1 plus I2. So which ammeter has the largest reading? Ammeter X is the ammeter that records I1. Ammeter Y, so let's circle them. So this is ammeter X. This is recording I1, the blue current. Ammeter Y is recording I2, which is the black current. And ammeter Z is recording I, which is the main current, which is the combination of both. So obviously, Z has the largest reading. And I can take it a step further and say that the reading in Z is equal to the reading in X plus the reading in Y. But they don't really need that here, but you should know it anyway. So C is the correct answer. The diagram shows a cell connected to two 6-ohm resistors. The 3 currents I1, I2, and I3 are labeled. Which row correctly compares I2 and I3 with I1? So based on the previous problem, we've established that the main current here is, here they've called it I1. So this is the main current, I1. And it splits off into I2 and I3. So we can write an equation here that says I1 equals I2 plus I3. So I2 and I3 compare to I1 in what way? Of course, they must be both smaller than I1, since I1 is actually the sum of I2 plus I3. So each one of them must be smaller than I1. So D was the correct choice. 3 ammeters measure the currents in different parts of the circuit shown. The diagram indicates the reading on the ammeters. How do we know that at least one of the ammeters must be faulty? Of course, here, this must be, this current here, the 2 amperes, must be the sum of I1 and I2. So definitely the 3 amperes here is faulty. It should have been actually 0.5 amperes. How did we know this? Because the current from the battery must be equal to the sum of the current in the 2 resistors. So C here is the correct answer. The circuit diagram shows a simple circuit with a battery of EMF 6 and 2 bulbs, each of resistance 2. Which row gives the readings on the ammeters? Again, you might be tempted here to do a lot of math, but I can tell you without any calculations that this must be the correct answer. Why is that the case? Because there are no branches here. The current flowing from the battery sees only one path in front of it, one path ahead of it. So there's no variation in the current. There is only one current flowing through the circuit. It must be the same everywhere. And the only choice that has the same current everywhere is choice B. Any other choice has different readings for ammeter 1 and ammeter 2, and that doesn't work because, like we said, there are no branches here. There are no parallel connections. There is only one piece of wire flowing through the entire circuit, and therefore there is only one current flowing through the entire circuit. So B here would be the correct answer. The diagram shows a circuit containing 3 ammeters, P, Q, and R. Which statement about the readings on the ammeters is correct? So you should know here that P is the main current. So this guy is the main current, and this guy as well is the main current. So this is I and this is I. Then it splits into I1 and I2. So we know that the current passing through Q must be less than P and R because the red current is only a component of the main current in blue. So Q is less than anything. So here C and D tell us Q is greater. So Q is definitely not greater. So these are out. And P is equal to Q. This is also out. The correct choice here would be the reading on P is equal to the reading on R because P and R are both blue currents, which are the main current coming from the battery. So B would be the correct choice here. The diagram shows a circuit containing 2 identical lamps and 3 ammeters. The current in ammeter 1 is 0.3 amperes. Which row gives possible values for the currents in ammeters 2 and 3? So again, just to make sure you understand this completely, this is the main current flowing out of the battery and flowing in again. So I here would be the main current. And this current splits off into I1 in blue and I2 in black. And our equation here would be I equals I1 plus I2. So if the current in ammeter 1 is 0.3, then ammeter 3 must be similar to ammeter 1 because they both have the same current. So definitely not 0. And ammeter 2 must be less than 0.3. So this is definitely wrong. And the only correct choice here would be choice B. Ammeter 2 is less and ammeter 3 is equal. So B is the correct choice. Only one of the ammeters in the circuit is showing an incorrect reading. Which ammeter is showing the incorrect reading? So again, this is the main current I. And it is split into a blue current, I1, and a black current, I2. And we know, of course, that the red current is equal to the sum of the blue and the black. Of course, the incorrect reading here is C, ammeter C, because they should obey the rule I equals I1 plus I2. And we are given that I is 0.3 and I1 is 0.1 and I2, according to this guy, is 0.2. This works. This is a correct equation. So this value and this value and this value, they work well together. But the problem is with this value. So C here is the incorrect reading. A battery, an ammeter, a switch, a lamp, and a resistor are connected together in a circuit. With the switch open, the ammeter reads 2.4 amperes. When the switch is closed, this reading increases to 4. What is the current through the resistor when the switch is closed? So this is also a nice application of the concept. Again, this is our main current I to and from the battery. And it is split into two currents, blue and black. So let's call the blue current, excuse me, I2, and let's call the black current I1. And when the switch is open, that tells us that there is no I2. So when the switch is open, there is no current flowing through the resistor. The ammeter reads 2.4 amperes. So basically I1 equals 2.4 amperes. When the switch is closed, excuse me, I'm so sorry. No, the ammeter reading is here. So this is not I1, this is I. So let's write that in red so that it's clearer. The total current is 2.4 ampere. And this total current is the current flowing through the lamp. So it's also equal to I1, since there is nothing except I1, because when the switch is open, there is no I2. So you just imagine the circuit without the blue part. So both I and I1 are actually equal to 2.4 amperes. Now, what happens when I close the switch? So when I close the switch, I get I equals I1 plus I2. And we already know that I1 is 2.4 amperes. How do we know that this has not changed between opening and closing the switch? Because the current I1 is equal to what? The current I1 is basically equal to the voltage over the resistance. And the voltage of the battery has not changed. And the resistance of the lamp has not changed. So I1 cannot have changed. But I, of course, now is going to change because it is now equal to I1 plus I2. And that's what they said. They said the reading increases to 4. So the new I, the total I, because the ammeter here is placed in a part of the circuit that reads the total current. So the total current is now 4. What is the current through the resistor? So the current through the resistor is the blue current, I2, because this here is the resistor. So in this question, we're looking for I2. What is the value of I2? So this is a simple mathematical equation. 4 minus 2.4 equals x. X equals 1.6 amperes. Let me give you a brief summary of this question because I know it was a bit confusing. So there are two scenarios. One scenario with an open switch. An open switch here means that this part is just not there. And this ammeter reads 2.4 amperes. And since it's only one branch, one circuit, so we know that the current here is 2.4 amperes as well. Now, if I remove all of this and now I close the switch, what happens if I close the switch? I have two currents. I have this current here, which is the main current, and it's split into the blue and the black. The trick here is to understand that the blue current, I1, is still 2.4 amperes. Why is that the case? Because the voltage is the same and the resistance is the same. So I1 is still 2.4. And now they tell us that the main current I is equal to 4. And they want the current through the resistor. They want this current here, I2. So how do I get that? I just simply subtract these two together. I just do 4 minus 2.4. And the correct answer would be choice B, 1.6 amperes. And this brings us to the end of our video. I hope this has been useful. Thank you for watching.